Good afternoon, everyone. Good afternoon, Adarniya PVC Garu Arun Agarwal ji, distinguished guest Dr. Sampathkumaran, Professor Sheshubai, Dr. Vaitishwaran, all my other colleagues, postdoctoral scholars, students, and friends. It gives me great pleasure to introduce our third distinguished speaker this year, which just shows that our school is passionate in wanting to understand nature and how it works. And I am happy to welcome these visionary scholars that have come to our school to help us go from strength to strength. I now request Professor Sheshubai to come and introduce the speaker.
Good afternoon to all. I feel it's an honor for me to introduce a distinguished scientist, Professor V Sampathkumaran, who has been working in TAFR for several decades. Professor Sampathkumaran has got his degree BSc from University of Madras and master's degree from Annamalai University, and joined TAFR as a member of faculty in 1976. Subsequent to that, he has done his doctoral work under the guidance of a well-known experimental condensed matter physicist, Professor R. Vijayaraghavan in TAFR, and got his degree from University of Mumbai in 1982. He has worked on valence fluctuations in rare earth compounds for his degree, and later on he has been as a postdoctoral fellow as Alexander von Humboldt Fellow at Freie University in Berlin, and on sabbatical at Institute of Solid-State Physics, University of Tokyo, and then come back to his tenure at TAFR. During his long tenure there, he also served as chairman, Department of Condensed Matter Physics and Material Science, and Dean of the Natural Sciences faculty, and he had a brief period of the director of the institute as well. Professor Sampathkumaran has contributed significantly to the area of strongly correlated electron systems, superconductivity, magnetism, and multiferroics. He has co-authored nearly 390 research publications which are published in reputed international journals, and from his significant work he has received several awards, and he was a recipient of Indian National Science Academy Medal for Young Scientists in 1986, and he received Materials Research Society of India Award in 1996, and he was elected a Fellow of Indian Academy of Sciences, Bangalore, and in the National Academy of Sciences, Allahabad. He was awarded the celebrated Santi Swarup Bhatnagar Prize in Physical Sciences in 1999, and he was elected a Fellow of Indian National Science Academy, INSA, in 2001. He also received the prestigious J.C. Bose National Fellowship in 2008, and he was a Fellow of Third World Academy of Sciences and elected member of Asia Pacific Academy of Materials. And he has visited, in fact, our school several times, and as a research examiner of several research scholars working with different faculty like Professor Kaul, myself, and several others. He also given some lectures before, but here we are very fortunate to have Professor Sampathkumaran with us today to deliver the distinguished lecture on behavior of 4f-electrons in solids, which is a puzzle for decades. And with his vast experience on rare earth compounds, he will be enlightening us with the latest situation on 4f-electron role. Thank you.
First of all, a very warm welcome to dignitaries on the dais. Honorable Professor V Sampathkumaran ji, our distinguished lecture series speaker, Professor Bindu, Dean School of Physics, Professor Sheshubai Viteshwaran, Dr. Viteshwaran, and also our invited guests, dignitaries of the dais, respected members of university, faculty, staff, students, invited guests, students, ladies and gentlemen. It gives me immense pleasure in welcoming all of you to our university, which has attained a very unique place as a major institute of academic excellence in higher education and research. Today's talk is on behavior of 4f-electrons, a puzzle for decades. With my little understanding of chemistry, I thought, let me orient myself so that I can enjoy your talk. So I do understand the fourth shell and the electrons in the f orbital, and also how the orders of various orbits are placed in a sequential order depending on the energy. But what is so interesting about 4f is something we would like to hear from you. And for me, it is already very confusing. And let me make way for our expert, and I'm sure that the talk will engage, inspire, and enrich us on our understanding of complexity and challenges of these 4f electrons solids. On behalf of the University of Hyderabad, once again, a very warm welcome to all of you. May I request Professor Sampath to kindly take over the dais.
Good afternoon to everybody. First of all, I would like to thank the School of Physics, particularly the Dean, for inviting me to the very prestigious talk in this university. I would also like to thank Professor Seshubai for a nice introduction. I really got frightened when she read the CV. I hope I justify all the titles which she mentioned in my talk. And it's really, as Dean mentioned, I visited this place several times in the past, but not during the last 7 or 8 years. Somehow I could not come. But I'm really very, very happy to be here because one of the, probably the topmost university in the country, which we have to really be very, very proud of. There are many students passed out from here. They're doing extremely well in various places, something which is to the credit of this Central University. And I'm sure a lot of faculty members really worked very hard to shape up the young talent for the benefit of this country. I would like to congratulate all the faculty members of the past and present in this prestigious university. And again, I am very, very honored to be here. So I was told that the talk will be attended by students of BSc or MSc or integrated master's course, and I should make it basically from various disciplines. I should make it as simple as possible. But I was really, in fact, when I was to give the talk by Vaidishwaran, I wanted to give a seminar in the department to have a focused talk on some other subject. But it's my subject of my research is so complicated and it's not so easy to give a popular talk on this. But therefore, I was really skeptical when I was asked to give. But I thought I should take it as challenge, try to see what I can do, try to make as simple presentation as possible on a topic which is extremely complicated. This is one of the very, very active topics of condensed matter physics, modern condensed matter physics. As you all know, that condensed matter physics over a period of 5 decades has really seen a lot of challenges, and almost every year a new phenomenon has been discovered and novel materials have been discovered. In fact, really made a very big difference in the progress of even applications in our day-to-day life, including, for example, magnetic tape recording and things like that. So therefore, any fundamental research in materials, in condensed matter physics, always led to many applications in the past. In that sense, you may not be able to appreciate today the relevance of the work, but it has implications for the future, including energy, which I will probably mention, if possible, at the end. So therefore, my aim is a very tall order for me to give a talk, a popular talk, understandable to people from various disciplines, on a subject in which is 5 on which I've been working on for the past nearly 45 years. But I must tell you at this moment that we have a division of, physics, chemistry, mathematics, computer science, and biology and things like that. My background is actually chemistry, BSc, MSc chemistry. I was asked to work in physics department when I took up my research careers. First 2 years I was not very happy because, I did not know too much of physics, and I had to do basically physical, organic chemistry, that is a division. So I was very skeptical, but later on I realized that was a blessing in disguise. And what many of the chemistry knowledge we really acquired later on are very, very useful to do the physics problems, particularly materials physics. So in today's time, you will find that you cannot have a separation of physics, chemistry, mathematics, computer science. Everybody has to learn everything. This is a message I want to give it to the students who are just doing undergraduate here. You have to focus on all subjects equally. You cannot say, I want to be a chemist, I want to be physics, chemistry. Otherwise, it's very difficult to shine in modern science here. And this is very, very important message I want to pass on to youngsters in this audience. In the same way, when you study, for example, condensed matter physics, you have to at least have some level of basic knowledge, of reasonably basic knowledge of many experimental methods, also many computational methods, also mathematical skills and things like that. So then only you will be able to attack a problem. Of course, we want to do specialized particular direction. It is possible at a later stage, but one has to learn. Therefore, today's science is very, very challenging. At the same time, we have to tune ourselves that we have a basic knowledge. We have a tendency, this elective is very boring, I don't want to attend to it. Focus only on the chemistry or only physics. That won't work today. So, and that way I would say the place like University of Hyderabad School of Physics, I would say that emphasizing fairly good exposure to many branches is something which I think young people really should make use of, the opportunities available in a place like University of Hyderabad. So anyway, having said that, I want to focus on my talk, and I would like to say that at the beginning that I'm not going to present any detailed data. However, I will show you the graphs. There are some experts here. There are faculty members who have worked in this, roughly in this field. When I say make a statement, they will be able to see what is on the screen. They can make out. But not everybody will be able to probably make out, particularly students. Therefore, I'm going to give you a story. Whatever I want to say, I'm going to tell you a story, rather than going into too much of technical details. Therefore, just listen to me. If you don't follow what is on the graph, that doesn't matter. Okay, so so what I plan to do is that when you have an electron, when the electron put in a solid, how does it interact with its surroundings? That is basically the fundamental issue in solid condensed matter research. And depending upon then you have the variety of properties and use those properties for your application. But the fact remains that the electrons which talk about, what kind of electrons you're talking about, where does it lie, how does it interact, this is a very, very challenging task. The knowledge which you had 100 years ago was different the knowledge we gained 50 years ago. What you gained not 50 years ago, not the same 30 years ago, 20 years ago, 10 years ago, 5 years ago. You could see a dramatic drift in the understanding which you had, and you find never-ending problem. And this more so, this particular point more so when you come to transition metals, which let me show the periodic table here. I'm sure I thought I was wondering where to start, because you have people from all disciplines. This is a periodic table which all of you know that, this is basically the elements which I'm going to talk about is basically the middle of the periodic table. There are 3D elements and 4D elements and 5D elements, and you have something like called 4F and 5F elements. And when you talk about magnetism, again I'm going to put emphasis on magnetism. Again, I have to focus somewhere. And basically you are talking about the 3D electrons in the case of iron, for example, cobalt, nickel, 4D electrons here, 5D, and 4F electrons in the case of rare earths, 5 electrons in the case of actinides. So the story which I'm going to tell for 4F is almost same what you have faced in 3D systems, except that the parameters which you deal with are totally different. For example, if you go from 3D, systems, for example, iron, cobalt, nickel, and actinides and 4f, you will find the orbitals which are really important for the magnetism. For example, 5f, 3d, 5f, 4f. There is a tendency that what really determines the properties of the material is that how far the orbital is lying away from the core of the ionic core, whether inside the ionic core or outside the ionic core, how well interacting with another ion in the lattice and things like that. Therefore, you could see the traditional knowledge 50 years ago was that in the case of transition metal, the 3D is just almost outside the ionic core here. The circle I'm just drawing the ionic core. And actinides, 4f is trying to, 5f is trying to be a little bit outside as well as inside. In the case of rare earths, it was believed till 5 decades ago, the 4f electrons are really well within the ionic core. Okay, by that I mean, okay, this is basically rare earths, which I'm going to, what I'm going to talk about is, I'm going to make the points concerning the physics of the f electrons here. The f electron systems of called lanthanons. Starting from the lanthanum and what is the atomic number going up to 71. Okay, so these are the elements which I'm going to talk about. Lanthanum 57 to lutetium 71. What is actually changing in this case is that the outermost configuration of the so-called valence electrons, which are supposed to contribute to bonding, that is 5d1 6s2, and then you have what is really, nothing is happening here. What is really changing the number of f electrons here? Okay, it varies from 0 here to, for example, 14 in the case of lutetium. It is increasing here. When such a thing happens, you will find that rare earth is, if these three electrons are lost for chemical bonding, then you call the system is, the rare earth is, for example, the trivalent. Therefore, if you read the textbooks of world textbooks, you probably even today, I think the knowledge is not completely changed in the text. Many textbooks is that if you say trivalent, is you say this, for example, gadolinium, if the trivalent number of electrons in the 4f shell is 7. Therefore, valency is a definition of the number of 4f electrons in the shell. So, therefore, if you tell the valency, you can tell what is the valency of what is the number of electrons 4f. That was basically the knowledge which we had 50 years ago. And it is possible that what is interesting to note is that even today theoretically is not very well understood. At the beginning of the rare earth series and the middle as well as the end, there is very unusual stability of the 4f orbital. There is a tendency to go more towards unfilled, half-filled and fully filled. This is not completely theoretically understood. Therefore, you could find some of these elements like samarium or europium, they have a tendency to exist in another state, 4f state. Instead of 4f n, it can have 4f n minus 4f n plus 1. Okay, and therefore it is called so-called divalency here. Similarly, cerium, it can lose its one electron here, then for chemical bonding, then people used to call so-called tetravalency, because you have an extra electron contributing in addition to 3 electrons here. Okay, so this is basically the table for those who are interested to know. When you go from C, if you say only trivalency of the rare earths, you have well-defined spin quantum number, orbital quantum number, and the total angular momentum, and then what's called GJ, Landé-G factor, and then you've got de John's factor. The de John's factor is defined by this. By that we mean that if you know the properties, for example, magnetism or magnetic ordering temperature or resistivity behavior, if you know what it is for gadolinium, in principle you can say what it is for other rare earths. In fact, the de John's got Nobel Prize about 10 years ago because he has had several systematics he established in condensed matter physics. This is one of the correlations which he proposed, that the property should really scale with reference to gadolinium in a very simple-minded picture. Okay, we call de John's factor. This was based on the assumption that the 4f orbital, which I am talking about today, is very well localized. Okay, so with reference to the outermost orbital. And as I told you that 5d 6 electrons have gone for bonding, and what you have is 5s 5p, the outermost orbital, which are filled, and you have their 4f electrons which are deep inside the ionic core. And if you look at for gadolinium, you put one gadolinium here, if you have another gadolinium here, this is the place where you have the chemical bonding here between, for example, the metal GD middle of the distance is somewhere here. You at this place you will find the 4 of electrons, or the density is the radial distance function as function of distance is practically absent here. Therefore, you will find that 4 of electrons are not participate in chemical bonding. In other words, it is not supposed to participate any kind of even covalent bonding. They are strictly very well localized. Therefore, all the knowledge which we had 4 decades ago 5 decades was based on the fact that these 4 of electrons are very well screened by the outermost electrons 5s and 5p. Okay, this is called localized picture of 4 of electrons. And this is not the case when you come to actinide. The 5f is a little bit outside. In the case of rare earth, in the case of transition metal, 3D, which is a small magnetism, it is actually participate directly in the chemical bonding. There is a fundamental difference between 4f and 3D here. That is why this makes it very interesting. The 4f turn out to be quite interesting. Okay, now the problem here is that the 4f, okay, I want to finish, bottom line of my talk is that this belief that the 4 of electrons really deeply within the ionic core is no more valid. That is basically the conclusion of today. There are several experimental signatures pointing to that. How does it look? How does the 4 of radial distribution function look like? There are several proposals in the 80s and 90s. I will not go into detail. The fact remains that the 4 of radial distribution function, it is really moving out here. Sometimes it looks like this, sometimes you find some density here. Okay? So this is the crux of the problem here, and there are consequences. Therefore, what I am going to tell you is that how do you arrive at that conclusion? What is the historical background over a period of 5 years, and what is the current status today? That's what I am going to say. So the most important properties or phenomenon, don't worry about the names here. I just listed one names which are being talked about in the literature, resulting from the tendency of the 4 of orbital to be localized, that is close to the nucleus or away from the nucleus, to be somewhere near the bonding region. Because of this, you have different kinds of phenomena. One is talking about, one is valence fluctuations, or mixed valence or intermediate valence, Kondo effect, heavy fermions, Kondo lattices, eternal magnetism, and spin fluctuations. And of course, there are other consequences for other phenomena. On I just mentioned one transparency later, unconventional superconductivity, giant magnetoresistance, metal insular transition, topological insulating behavior, multi-Fourier, geometrically frustrated magnetism. There are all kinds of phenomena which were discovered subsequently in condensed matter physics. You will find that whenever you have a rare earth, and you will find there are complexities due to the tendency of the 4 of electron to have this ambivalent behavior, neither localized nor localized, or both ways. We don't know how it behaves. Okay, therefore my focus of my talk is to talk about the 4 of localization, delocalization phenomena and a historical perspective on this. Okay, all my transparencies I told you is not for you to read, because I just do the cut and paste my PDF file, because the nature of my talk is that, I cannot ask you to read or look at my data. Just therefore, just listen to me. These are 2-page paper in physical review B. Now I am going to give us a very interesting historical background. So look at the simplest metal, cerium metal, supposed to be simplest metal in the periodic table, particularly in the rare earth series. So this metal, 1910 or 1915, there is a very famous physicist by Bridgman. I think faculty members know that. I want to tell the students, he is one of the major discoverers of the high pressure physics. He is a pioneer of high pressure physics to do the experiments under high physics. He tried various materials in 1910, and we tried cerium metal, which is supposed to contain one local 4 of electron. He applied pressure on the material. He found some sudden volume change at about something like 12,000, close to 12,000 atmosphere, 12 kilobar. So, and then it took different cerium, different batch. You find the results are not reproducible. So you were just trying to getting confused, left it like that. Subsequently, another group did the experiment. They are able to repeat that same data, but of course different pressure and different magnitude of the volume change and things like that. And they found the structure is simple face-centered cubic, but there is no structural change. Even under pressure, structure remains same. Okay, but suddenly the volume changes somewhere around 12,000 kilobar. So that was a puzzle and it was left out. And these authors, I mean, again performed the experiment. Don't read, forget about all these numbers here. So, the 1949 is a 2-page paper. You don't find even for an abstract. Today, if you submit a paper of this type, it will come back immediately. There is not even abstract. You see how the science was done those days. It was very informal. So, not even abstract here. This is just 2-page here. And look, I want to read only this particular part. I mean, they repeat the experiment. Today, if you repeat the experiment, send a paper to your journal, people say you are repeating the experiment. What is new in that? So, the same experiment repeated for 30 years later. And they only thing is they went to some theoretician, went and talked to a theoretician, and his name is Zakarianson. There is also Pauling was involved. In fact, there is a review article in 1970s, Gestner's review article. He refers the name of Pauling. Somehow he did not mention. Maybe there is another paper Pauling's name is mentioned. So it went to Zakarianson. Zakarianson proposed the idea that the possibility that cerium is you're losing its 1 electron, 4 of electron. You start with 1 4 of electron. Under pressure, you're losing 4 of electron. Therefore, under pressure, there is valency is changing. So-called, in the old terminology, so-called valency is changing from 3 plus to 4 plus. So, he said it is not absurd because cerium dioxide, cerium O2, valency is 4 plus. I mean, in the old terminology. Therefore, that is a possibility. And look at it here. As a result of stimulating discussion, today's time we will demand authorship. Or at least acknowledgement. Here, neither not even acknowledgement here for him here. As a result of stimulating discussions with our colleague Zakarianson, we propose the following simple model to explain this rather unusual transformation. Cerium, which is the first atom periodic table to permit the extension of existence of a 4f electron in the free gaseous state, when condensed, that is when applied pressure, exhibits the tendency to become perverted from a trivalent to quadrivalent state. For example, cerium oxide is possible here. So therefore, it was assumed that the electron is completely lost to the conduction band. It becomes cerium 3 plus to 4 plus. Now, subsequently, the large number of people worked on this. They arrived at a phase diagram. Again, I will not go into all the details. This was supposed to be a phase diagram of cerium. Okay, and if you look at the phase diagram, you could say that as a function of temperature and pressure and temperature, you would see we have a phase called gamma phase in the phase standard cubic. The alpha phase, which is also phase standard cubic, there's an intervening phase called hexagonal closed packed structure, a completely different structure here. And there is high temperature, another phase which is also superconducting. This ignore, this also ignore now. The basic point here is that this particular line attracted a lot of attention in 1670s to understand what is the nature of the contraction of the volume. The reason why people are not, some people are able to reproduce the valence, the volume contraction, some people could not reproduce. The reason was that, and also the so-called, what they call impurity, was that there is another intervening phase there, beta phase, and which is a completely different structure. Therefore, people are getting very messy results those days. And after very careful investigation, people that you could even room temperature, you apply pressure, you are going from going an isostructural phase transition from a gamma phase, which is a high volume phase, to another FCC phase, which is a low volume phase. The structure virtually remains same. So therefore, the consensus till 1965 was there is possibility that there is a complete transformation of electron from 4f completely gets delocalized. From 4f it goes to 5d and becomes the conduction electrons. Okay, the problem came again. You will have all such bad transparency. Therefore, don't try to read here. I just want to show the PDF file. There is a paper in 1965 by a Russian group. That was a paper of a Russian journal, and that was subsequently translated in Soviet physicists translated English version. And those authors measured samarium hexaboride. Samarium hexaboride, God knows why they measured samarium hexaboride. That material was not at all interesting those days. Today, samarium hexaboride, which was found to be interesting in 1965, today, even after 60 years, it is attracting a lot of attention completely from different angle. I'm a little bit jumping. That the field of topological insulators. So I will come to that later time permits. So what I want to say, one material attracting attraction for a period of 6 decades. Now, the primary result is this. These authors, what they did is, again I am going back to my original statement, that when you do it experimental science, also theory, you have to have we have to have knowledge of many experimental methods. Okay, also in theoretical tools. You just cannot manage one. So then only you can have a combined picture of the physics. This is what I'm going to demonstrate in my talk. How many text experiments are used? Therefore, I won't be able to give the, I won't be able to tell you what is the experiment, how it is done. But I'm going to give you only one line, what that experiment measures. This experiment basically X-ray absorption technique. In this technique, what you are trying to do is that you are trying to create an intra-atomic transition. You are removing 2p electron and putting it in the 5D shell of cerium. Okay, so therefore the transition energy is involved. So, therefore, what was known is that people tried different materials and they say and they concluded there is a difference of something like 6 or 7 electron volt if the 4f orbital electron count is different by 1. In other words, if you take samarium 2+ state, okay, you do X-ray absorption, you will get one peak here. Okay, so one peak. If you take 3+, you will get one peak, but however the position will be shifted by something like 7 electron volt, typically 7 electron volt. What these authors found was that they found, forget this particular part, this is due to extended fine structure that is not relevant for today's discussion. They found 2 peaks separated by 2 electron volt. And this, if you compare some standard compounds, some samarium compounds, they find that it's as if this compound contains both the valence states, both 2+ and 3+. Okay, but therefore, what they conclude you cannot read here. What they make a statement. You look at the abstract here. The abstract says this. By the way, there is only one site for samarium here. This is a cubic compound, only one site. They concluded, despite the fact that all the sites are crystallographically equivalent. Okay. Samarium exists in 2+ and 3+, 2 different valence states. In today's time, you send a paper, referee will immediately ask a question, all they are chemically equivalent. How can you have 2 different valence states? This journal published it, they left it like that. We are getting in the crystallographically equivalent state of positions, you are getting 2 different valence states. So they left it like that. Okay. Therefore, this, as if this compound is the mixture of 2 valence states here in this. And okay, now the problem came, again I'm going to Mossbar, various techniques, Mossbar technique. And people did Mossbar experiments in late 1960, following that work, 1969, people did Mossbar experiments. Mossbar experiments told you, it does not give an evidence for both the valence states together. What it showed you, what you measure in Mossbar is what's called parameter called isomer shift at the nucleus. This basically is electron density at the nucleus, and experts will know that S electron density depends upon the 4f occupation number, how well the 4f is screened by the output, like how many number of electrons you have in the 4f shell, and how the outermost orbitals are screened. Outermost orbital screened by this inner 5 electron. Therefore, if the number is varying, the 5 electron, the outermost s orbital contract, for example, outermost NEF. So you will find S electron density variation that will be measured by isomer shift, and that isomer shift you find, if it is 3+, you should get an isomer shift somewhere here. If it is 2+, you should get somewhere here. What they find is lying somewhere in between. Okay, somewhere average. And also look at magnetic susceptibility. You will find that it is some kind of average of both the valence states. However, when you say average, but it does not. It has neither the characteristic of 2+ nor the characteristic of 3+. It is something else. For example, samarium 3+ should have ordered magnetically low temperature, and here there is no magnetic ordering here. Okay, susceptibility shows a peak and then tries to come down here. This is something very perturbing people. A completely different low temperature behavior. Though at high temperature, it looks there's an average of these 2 valence states. Okay, now. Therefore, subsequently, many groups started working on samarium compounds, try to understand whether any other samarium compounds behave like samarium hexaboride. And this is where these are really a landmark discovery. This particular paper is a landmark discovery which turned out the big turnaround in quantum matter physics, at least in magnetism. That the Jayaraman, who is a nephew of Sir C.V. Raman, and there is a story about that. I'm not going to tell because I want to be a little careful when you go for public talk. So anyway, he left CNR, C.V. Raman, C.V. Raman, he was a student of C.V. Raman, he was nephew of C.V. Raman, he left Bangalore and went to Bell Labs. He went abroad, did PhD, and he joined Bell Labs. And after seeing that work on samarium hexaboride, he tried to study some of the divalent samarium compounds, like in cerium. He's an high pressure specialist. He want to apply pressure and see whether he can bring out features similar to what is the samarium hexaboride. What he found is that samarium sulfide is behaving differently from samarium telluride and other chalcogenides. You could see there is a very sharp, with these electrical resistivities from the temperature, there's a sharp variation around 6.5 kilobar here. Okay, and then of course hysteretic, they essentially first order phase transition here, whereas samarium other telluride, there's a continuous phase transition. But the fact remains, the basic conclusion is that the ambient pressure phase is semiconducting, whereas high pressure phase is metallic in both the cases. Therefore, there's a metal to semiconductor metal transition under pressure. The color of this is black, whereas the color of this golden color. There's a dramatic change in color. Okay. Therefore, he proposed the idea that this behaves like, in some sense, samarium hexaboride. And later on, people found out that the properties of samarium sulfide under pressure is exactly same as the properties of samarium hexaboride. The point here, it looks like average of 2 plus and 3 plus at low temperature. It neither corresponds to 2 plus nor corresponds to 3 plus. The system has got completely demagnetized. It's supposed to be magnetic. It is completely lost its magnetism at low temperature. That was a big puzzle. So these authors subsequently came out with the idea of the 1971. The Maple and Willoughby unfortunately died in a car accident about 10 years ago. Both of them are very good friends of TIFR. They know very well. He's right now he's still active academically, one of the leaders in quantum matter physics. Brian Maple in University of California, San Diego. They proposed the idea that they were the first one to propose that the 4 of electron is hybridized with the conduction band. Net result is that there's some kind of very unusual state formed, and that state need not be same as what you have in 2 plus or 3 plus. It gets demagnetized. So they are the one who propose the idea that there is a spontaneous electron movement of electron from the 4f shell goes to the conduction band and comes back to 4f shell. It keeps fluctuating back and forth as a function of time. And they also analyzing various data. They put up gave a time scale is of the order of 10 to the minus 13 second, minus 12, minus 13 seconds. Therefore, it was concluded that you have spontaneous fluctuation between the 4f shell and the conduction band for the 4f electron. Therefore, net result is that it cannot be magnetic because there is no stability of the 4f electron in a particular shell. It does not know what it should do when it is fluctuating. So anyway, therefore, what we actually measure depends on the experimental techniques. What is the time scale experimental technique? If you measure mass bar time scale is basically the time scale of excited state lifetime. It's minus 8 second, typically minus 8 second. Whereas electron spectroscopy time scale is something like minus 15, minus 16 second, and the time required to knock out the electron from the shell. Therefore, you will find that if you use a very fast technique, you will see the snapshot of both the configurations. However, if you take a very slow technique, you will see an average. So therefore, the explanation given was by Dales and Wilbur that look, you are getting contradicting results for samarium sulfide, samarium hexaboride. We use different techniques. The reason is that you are using different time scales involved in the experiment. For example, if you look at photoelectron spectroscopy, this is a samarium arsenide which is trivalent. Okay, I will not go into the detail here. Here, as you know, for X-ray absorption involves transition of electron from 2p to 5d, the transition energy. In this case, same photon, using photon, knocking out the electron and looking at the kinetic energy. And you can look at any orbital in your atom. Therefore, in this case, we are looking at the 4f orbital. So you are knocking out the 4f electron and try to look at what is left in the system. And this is called various final states, various states left behind the excited state. This is a fingerprint for the trivalent state. Similarly, for divalent state, is another fingerprint here. And you will find here, this one here, you will find this is a mixture of both the configurations, F6 and F5, two valence state configuration here. So this is therefore conclusive enough to suggest that that the time scales are very, very important. And okay, let me skip that without confusing you, but still I should mention that this somehow this system thulium selenide, same problem happened thulium selenide, but the problem here thulium selenide turned out to be magnetic. Okay, here also say your electron goes out and comes back in the same time scale, but this created a lot of confusion. Why is it ordered magnetically at low temperature? Similarly, it was found out that by this group in Bell Labs that on the surface it is can be divalent, on the bulk it can be trivalent. It could mean even surface valence transition. This has relevance to the current topic of topological insulating behavior. Let me skip that. And I just want to mention that we are one of the early birds to get into this field. And those days we not photoelectron spectroscopy. We used to go to IIT Bombay, and I also collaborated with CNR of photoelectron spectroscopy. We measured, we found out new new materials where you will find there is actually a spontaneous fluctuation of the 4f electron between valence and local 4f orbital and conduction band. That's not important. Now same thing is found, for example, even in the case of europium, this is our work which we published here. You could find the 3D photoelectron spectroscopy. You will find that 2+ component and 3+ component, they are varying with temperature here. Okay, in this system, both the components exist together here, which is very strongly temperature dependent. That's temperature. You could see that it's not only it's not a fixed number. So it can also vary with temperature. You know how much time it stays in orbital. What is the average net valence occupation number? It can vary depending upon the temperature. This varies from material to material. This is to show you some more work, X-ray absorption in collaboration with IITs in the material. So anyway, now the most interesting material even today is which we discovered in our laboratory. Actually, is my thesis work. This work was done. We found out that magnetic susceptibility as function of temperature for one material, europium palladium silicon 2, is very, very funny here. There's a maximum, it comes down. One would generally dismiss it by saying it's due to some magnetic ordering. And however, if you look at susceptibility in absolute terms, it is intermediate between this divalence, is a divalent reference, which is shown here number. This is the number for this side. This in between for value which expect for divalence and trivalency. And you will find, therefore, we concluded this intermediate valent. What is surprising is that this number, susceptibility, make a big sharp change here. Therefore, we guessed that there is a strong possibility that even the 4f occupation number is changing a lot around a very narrow temperature interval. Actually, this work was done in collaboration with R.J. Pillai and Diware in TIFR. They did mass bar spectroscopy, and they found again isomer sheet, which I told you gives you information about the occupation number or the 4f shell. Is that you look at this dramatically varying as function of temperature. If you take any material, if you do mass bar spectroscopy, if you do temperature dependence, it should be extremely weak, what is called thermal redshift. Okay, it's much less than 0.1 millimeter per second. It is basically flat as function of temperature. Whereas you could see here it's going all the way from a number which is very high, a very low number here. That transition happens at a very, very short temperature interval. Okay, that means, and then you can derive the occupation, 4f occupation number or valency from this using some model, and this is plotted here. You could a dramatic variation in such a narrow temperature interval, depending on the model or techniques which you use here. Very narrow temperature interval. Even today, this is an exceptional compound in the history of rare earths. A sharpest variation of the valency of europium, average valence of europium in a narrow interval. In other words, I would like to say that 4f orbital does need not have a stable 4f configuration. It can vary as a function of time. Okay, and that when you take an average, time average, and that number also can be temperature dependent as function of temperature. Therefore, the concept of valence which you talk about in the textbooks is completely different. It can be, it's not a very stable number. So it's a very sharp valence change here. Okay, so now, till now I gave examples of europium can undergo some kind of 4f electron delocalization, samarium, and things like that. People are still bogged down with the idea of cerium metal. Why is it cerium? What is happening in cerium? So people are trying to look at also many cerium systems, and when you're trying to study many cerium systems, they found something much more unusual. that if you measure heat capacity of this paper appeared in solid state communication. Okay, this is again a very landmark paper in the history of rare earths. Is that this compound, if you measure heat capacity as function of plot as a temperature, you could take a linear term here. This linear term is very huge, something like 1.63 millijoule per mole K square. And if you get the density of state derived from that, it is compared to simple metal like copper or aluminium. It is 3 orders of magnitude large. Okay, despite this compound is non-magnetic. So this is a very, therefore, as if you have at the Fermi level, this comes from the density of states at the Fermi level, as if Fermi level contains huge density of states. So this also actually proposed some explanation, but the fact that the terminology used was heavy fermion, which was discovered later, the very heavy electron. This is again a very landmark discovery. In the Fermi level, you don't expect such a very strong, electrons which are conduction, which are free to move. They are not supposed to be heavy. I mean, in a very loose terminology, electrons can, when somebody can move from one place to other, that means they are not very heavy, right? So if somebody is very heavy, will not be able to move that fast. Therefore, these electrons are supposed to be conduction electrons, and you will find that they have become really very heavy. There's a contradiction here. So therefore, I mean, this was a great puzzle here. And if you look at the physical properties, various physics, in condensed matter physics, solid state physics, those who have studied students, take a simple metal. There's a correlation between heat capacity, the electronic contribution, and the magnetic susceptibility, and the electrical transport. There's a coefficients involved. There's a correlation. There's a ratio. So therefore, they are trying to look for the ratio of that corresponding terms in susceptibility, corresponding terms in resistivity, and they find even those terms also are got really enhanced. I mean, again, I don't want to go into the details. You could find that there is a susceptibility here. The point here, high temperature, you have a strong local moment. I mean, as if it is magnetic. There is a very strong 1 electron, 4 of electron is strongly magnetic. But as you go to low temperature, you are losing that magnetism. Okay, as it looks as if it's non-magnetic. So, I mean, the terms, the changeover of the even statistics, Bose-Einstein statistics, Fermi-Dirac statistics at low temperature. Also, in the same way, if you look at the electrical transport, there is a coefficient of T square, which comes into picture. That is all they're getting enhanced. Therefore, you find all the parameters which you normally expect for simple metals, they are really got enhanced in this metal. Otherwise, they look like simple metals. Okay, various other things. So this was a puzzle. This is called a Fermi liquid behavior. And then now, therefore, there are a lot of attempts to study many other cerium compounds. Again, this is again a very landmark discovery, which is really a big turnaround in condensed matter physics. Is that I want to tell young students, any small observation which you make, you should not ignore. You should be very serious to do the experiment. Even a small glitch, you should not try to do 10 point. These computers do a 10-point average and give the plot. Don't do it any averaging. You look at the data as it is, and you will find that small feature which is very, very crucial. This particular author, Steglish, was Uleban, who is again, I mentioned the point, who first proposed explanation for 4 of electron delocalization. They were studying this material. This is non-magnetic material. This is the one which contains 1 4 of electron. And they wanted to see whether it behaves like cerium metal or something else. And they found they behave exactly like cerium aluminum 3 in all aspects. But what they found in this material is at low temperature, they found a drop in resistivity. The drop in resistivity almost going to 0. In some, they prepared n number of compounds. Only some compounds, only some samples they will find the drop, not in others. So therefore results are not really reproducible. They found some kind of superconducting transition in the material. And in fact, if you see the paper, this journal directly by this vanished. This journal doesn't exist anymore. It's one of the very famous material, those journals. This has come up in the form European Physical Journal B now. So they published in this journal, however, with a footnote saying that they are seeing a resistivity drop at low temperature, otherwise behaves like cerium aluminum 3, and high temperature there is a magnetic 4 of electron. At low temperature, if you look at it, it looks as if there is no 4 of electron. Okay, it has become a band like at low temperature. But however, they see a drop at low temperature, superconducting. So they don't know how to explain that. They left it as it is. And then in the meantime, Steglish moved out of this lab in Cologne. He opened a new institute, Max Planck Institute at Darmstadt, and he pursued it. It's a 3 years of work. And this is a work, technically, I mean, people say there is Nobel Prize winning work because he made a dramatic paradigm shift in the understanding of magnetism or superconductivity in general. So they found that whatever they found in one or two samples, they really pursued again they prepared hundreds of samples, and they do find yes, there is a drop in resistivity. But they are not able to see that by other techniques like susceptibility. In this, they found by susceptibility, also by heat capacity. There are anomalies associated with superconducting transition in this material. The anomalies are huge. Okay, and if you take any other superconductor like aluminium, you expect a jump in heat capacity. Okay, in this case, the jump is very huge. All the parameters are really got magnified. The huge jump, giant changes in the parameters which you have to have for superconducting transition. So therefore, they propose a very, very modest title. By the way, I just want to mention to you that whenever you have a local 4f electron, when superconductivity was discovered in 1911, and a lot of materials were found, I mean, in which if you have magnetic element, superconductivity will be killed. Therefore, it was believed that superconductivity and magnetism cannot coexist. Also, if you have local electron, local magnetism, even if there is no magnetic ordering, that should kill the superconducting pair. Therefore, you should lose superconductivity. So, therefore, both the phenomena will not go together. So, therefore, these authors were very afraid to publish the paper. But the fact remains that they see in superconductivity in the same system in which you have a very large magnetism. Therefore, strong polyparamagnetism. When I see strong polyparamagnetism, as I told you, aluminium, copper is polyparamagnet, and enhanced susceptibility is called strong polyparamagnetism. So you will find the superconductivity in the presence of strong polyparamagnetism, but which will not be accepted by the community. They have a very tough time in publishing the paper. He said, how is it possible? You cannot have a strong polyparamagnetism coexisting superconductivity. So that paper was rejected by PRL a few times, and more so because at the end of the paper, he said, today you cannot send the paper to any journal and get it published. They say that we pressured some n number of samples. We see in 5 samples this feature, not in these 5 samples. I mean, nobody will, in the end of the paragraph, we prepared in fact, I prepared more samples. Take list 2 cerium copper to silver samples of same quality as indicated before, which show a somewhat reduced coefficient gamma, their heat capacity, and specific heat jump of BCS size. So far, one of these samples was studied to magnetization. This has some volume fraction of susceptibility. Okay, but they are not able to see. So although our preliminary results with the new samples form quite convincing case, we would welcome a confirmation by other workers of our conclusion that cerium copper silicon is intrinsic superconductor. So they are not really very confident. Okay, so I mean, it's just those days even journals really used to appreciate, even if you're not confident, as long as what you see, you believe, you publish it. Today I cannot do it. You will say, please repeat with experiments. Okay, you are not confident of that. So this paper really make big difference in the magnetism. If this paper was not published, today you will not have the field of heavy fermions, superconductor. Okay, therefore I just want to bring it to your notice. I just want to repeat the point that if you are confident that results are correct, if you are referee, accept it. Yes, authors are truthful. Yes, accept that they are saying something. If you are an author, you be confident to say what you are observing. Doesn't matter where it is published. And this, in fact, I know both the referees also. I know referees were very angry when the published paper was published. The referee himself told me this, and then the authors also know who the referee is. So they were enemies for 20 years. So now this is a big, there's a big turnaround in this field. Anyway, basic point what I want to say is that sometimes if you do the experiment very carefully, as I told in the very first paper, they saw only 1 samples out of 10 samples, but they put a footnote and they could have left it. The fellow moves out to another place, repeats the experiments on several samples, and then focus on 2 samples and come to the conclusion. Then even they had a problem. Fought with the people, finally got published. So anyway, this is a good lesson for all of us. You know, it is this paper which coins the term heavy fermions. The reason is that if you look at electron heat capacity, which is very huge. That is, density of state is very huge. And superconductivity is coming from the same electrons which are responsible for magnetism. From where the magnetism is coming, same electron is responsible. Okay, only thing is they got hybridized with the the conduction band. It is a completely different band structure in this material. Therefore, the term heavy fermion was coined by these authors in 1979. So that is how this field was born. Okay, at this moment, I would like to say that again, many people are trying to study many materials of cerium. Let us see cerium, copper, silicon, heavy fermion superconductor for the first time. Okay, the electrons are not supposed to be superconducting; they are superconducting. The heavy electron is become superconducting. So people are trying to study various systems. Electrons are getting dehybridized. How is it possible, and what is happening? So people are trying to study many cerium systems and trying to do that. There are another very funny discovery, and there is a conference in Santa Pura which I happened to attend. And the same the pioneer Uleban who proposed a very remarkable finding, and people thought he is a mad person. But the reason is that cerium dioxide. He studied simple cerium dioxide insulating material. Cerium dioxide, he measured electron spectroscopy, and he found that he reported the cerium dioxide is not showing tetravalency. As I told you, if you lose 2 electrons, 4 electrons here, cerium, if you look at it, cerium is 4 plus, oxygen is 2 minus. Therefore, it has to be a 4 plus. Okay, but if you do it with many, then there is no magnetism in cerium in this, because there is no 4f electron. So this he proposed the idea, and he said, and then he proposed. He took a large number of cerium compounds, and he found that you cannot find even a single tetravalent cerium compound. He said that there is no tetravalent cerium compound in the world, the universe. So that created a lot of furor, and the people, and he also did thermodynamic calculations. He said that you cannot extend average valency of 3.3 for any cerium compound. And again, people pursued that idea, not that left that out there, and it was found out that one of the very important point that was made by using various experimental methods, I will not go into the detail, is that the 4f, very interesting point of the behavior of 4f was found around early 1980s, is that some 4f electrons can occupy place which is very close to nucleus. Some can have an extended character. They can participate in bonding. Bonding in the sense they can also present in oxygen 2p orbital. And then when people try to do the spectroscopy at oxygen, you sit on oxygen, do what is called resonance photoemission. Okay, I will not go into the detail, and I think I have a figure here. I will not. It is called resonance photoemission. We will get confused if I show so much of thing. This is a resonance photoemission picture. In other words, you sit on oxygen valence band, and you carry out a transition from 4d of cerium to 4f of cerium. Okay, when you do that, you will find oxygen 2p is getting enhanced, oxygen 2p emission. Therefore, that suggests that you have 4f electron oxygen band. That means that you have an extended 4f character. 4f has not really lost its 4f character when it bonds with oxygen. Therefore, the community has come to the conclusion that you have to have 2 different kinds of 4f. One is localized, like in gadolinium, other one which is really delocalized, which is occupying the valence orbitals of other bonding elements. Therefore, this is a very important conclusion. Therefore, the question comes: what is the valence? I mean, there are of course a lot of further theoretical calculations. What could be, what exactly it is? It was conclusively established that you have 2 different types of 4f character in materials. So therefore, the definition of valence, in the beginning I mentioned, first transparency, the valency is a measure of 4f occupation number. That definition is leading a very misleading conclusion. Dioxide, if you say that it is 4f is valence is a measure of 4f occupation number, then it is not tetravalent, it is mixed valent, because some portion of 4f you find even the oxygen. So therefore, this is a really textbook material. I don't know whether it's gone to textbooks now. So cerium, you do have the 4f character. The original idea that 4f is really localized, close to the nucleus, is no more valid. There is something coming out, now sitting somewhere outside. Okay. So therefore, we have to redefine the valency, the concept of valence when it comes to such materials. Okay, I talk about what is called localized and itinerant. And when you have itinerant, it becomes there's some covalent bonding on hybridization. So this is one of the very important findings early 1980s, and I don't want to go into the details that we also found the same problem exists when it comes to European systems. Okay, people thought that okay, fine, maybe the beginning of rare earth series, maybe something may happen. We find this problem exists even when it comes to many other members. That it is, if you measure with some techniques, it looks like there is hybridization. If you look at some other technique, it looks like localized. Therefore, you have to talk about the concept of localization, delocalization when it comes to the rare earth elements. Okay, they're all data. I should skip that. Now, let me go to the next point, which I want to say that in metals, I think I had 5 minutes time, 10 minutes, 5 minutes time. 5 minutes, okay. So in metals, you have two different kinds of interactions. One, with the responsible magnetic ordering, what is called RKKY, where the 4f electron polarizes the conduction electrons, and the conduction electron density changes sign as function of distance. There is also another interaction called Kondo interaction, which is trying to kill magnetism. So this interaction promotes magnetism. This interaction kills magnetism. Okay. Therefore, if you take a material of cerium or any rare earth, you put a rare earth at every site, and you will have two different kinds of interaction. One interaction you will try to kill magnetism at every site, and another interaction try to promote the magnetic interaction at two different sites. So therefore, you have competition between the magnetic ordering and non-magnetism. There are the two opposing interactions. So the net result is that because of the local interaction, which we try to make it non-magnetic, that comes because of the strong hybridization. Hybridization means trying to make it non-magnetic, and there's the density of states getting modified here, as I already mentioned. Therefore, this is getting enhanced your large value of effective mass here. So, so these people are trying to play with this, and you find that there is one is called on-site interaction on same site, other one is inter-site interaction. Both have different functional forms. On-site interaction has a functional form like this. This is the interaction strength at the same site, the density of states. This is the interaction which is responsible for magnetic ordering, and you will have goes like interaction strength square. So both are different functional forms, and therefore if you have different rare earths, the periodic lattice in a compound, a lattice of rare earth ions, you will find here that there's a competition between these two, and net result is you have this kind of very interesting phase diagram. So if you plot the characteristic temperature, for example, magnetic ordering temperature, or the interaction responsible for magnetic ordering, TRKKY, or the interaction responsible for non-magnetism, TK, their functional form I've shown here, already gave the functional form here. You have this kind of format. You plot as a function of interaction strength, you will find at some temperature, the magnetism will disappear here at this point. Okay. So this is what is going on in current literature. People are trying to play with the tuning, the interaction of non-magnetism, interaction strength of non-magnetic interaction and magnetic interaction. You play with that, either applying pressure or applying magnetic field, do chemical doping, and all kinds of things you can do, try to play with that. And people found all kinds of very interesting anomalies. One of the most interesting anomalies is that if you tune the parameter, at some point, this is the magnetic ordering temperature, goes through a maximum. I will not go into detail. If somebody is interested, I can explain that. And then at some point, you are losing magnetism here. As I already mentioned, you have what is called, like any other simple metal behavior with enhanced parameter, that was fermi-liquid. And then you have at this point, what is called non-fermi-liquid. All the phenomena which you talk about simple metallic behavior, it breaks down. Conventional wisdom breaks down at the point where you are losing magnetism here. Okay. Today, there are many explanations. I will not go into the detail. The current people are trying to argue out for various reasonings. They are trying to explain what is the origin of what is called non-fermi liquid behavior. And the most interestingly, at the same point, you do find the superconductivity coming into picture, where you have non-fermi liquid behavior here. Therefore, you could see when this basic, by the way, this is a degree of delocalization. When I say the interaction parameter, the interaction parameter increases, you are increasing the degree of covalent mixing, degree of hybridization. You are increasing the hybridization of 4f shell, or increasing the tendency for delocalization. You are ending with a very complex behavior at some point in the magnetic phase diagram. One of the puzzles in the field how do you describe this non-Fermi liquid behavior? And of course, it was first discovered actually for uranium metal 1990s, and now it is found for many rare earth materials in this thing. And of course, there are various models which I think I should not go into detail. The one other exciting observation is that this is from our work. There are many materials which I don't want to detail. Is that the other important thing is very transparent. Anybody can look at the figure. This is electric resistivity as function of temperature. If you keep increasing the hybridization, at some point you will find that even the transport behavior is very funny with reference to other compounds in the same family. For example, if you look at lanthanum, we have one series, lanthanum copper arsenic 2, lutetium copper arsenic 2, yttrium copper arsenic. They look like sort of metals here. The resistivity as function of temperature. They are normal positive temperature coefficient. When you come to cerium, look at it. This is a negative temperature coefficient. Okay, it's a completely different behavior. I mean, there are many details. I should not go into the detail. If you look at low temperature, there are many funny anomalies here. Let me not go into that. But this is completely different, as though this is trying to become semiconducting here. So you could see when you have the moment you have 1 4 of electron, 4 of cerium, and it is little bit weakly hybridized, the transport behavior is trying to behave like almost like insulating. So this is called a Kondo insulator, Kondo insulator, Kondo semiconductor, and some of the Kondo semiconductor which we also discovered now the groups, a very famous group in Germany are pursuing. They are becoming very famous in topological insulator behavior. Another topic in quantum matter physics. So therefore, they really provide very beautiful opportunities to understand the consequences of the 4 of electron delocalization in solids. And the proof, for example, is not really a complete gap. There's a pseudo gap. If you look at photon emission here, this measured synchrotron with various photon energies, you could see there is a 4 of density at somewhere here. You will find the dip here is pseudo gap. It is not a complete gap. This is result is published in collaboration with a Japanese group, and therefore you could see there are many interesting features coming out due to 4 of localization. There are many unexpected features. Like for example, some are even ferromagnetic. You expect the ferromagnetism should really kill Kondo effect. You see ferromagnetism, and there are various other pictures proposed in literature. Whether 4 of electron, when you tune the hybridization here, whether 4 of electron are you losing suddenly hybridization here or somewhere here. So this is you are losing suddenly here. The one scenario is called local picture. Another picture is that you are trying to lose gradually. Very Fermi surface changing gradually. They're all little complicated scenes. I just want to tell you that it has the 4 of electron localization, delocalization. How does it affect the Fermi surface in metals? There are disputes in literature, and we are able to show in some materials that this picture is valid. It's a continuous process in this material. So slowly it's trying to become itinerant, retaining magnetism. It's called itinerant magnetism, band magnetism, and then it goes to the Fermi liquid picture. And so for example, I show typical data here. Cerium, rhodium 2 minus X, published physical to B. This is the N compound magnetic ordering. Another N compound here, it is not magnetic, Fermi liquid, in between a very complex behavior. So you could see many anomalies associated with the 4 of electron localization. These have been established even by photon emission. They're all detailed, which I don't want to go in detail. Therefore, I would like to say that the original belief of that the 4 of electrons or localized picture is no more valid. Therefore, the concept, the valency, assuming the 4 of electron is localized, is no more correct. So we have to introduce a different kind of language, and depending upon the degree of localization or delocalization of 4 of electrons, you end up having all kinds of complex behavior. You can also tune the degree of 4 of localization by applying pressure, even magnetic field, and also chemical pressure, chemical doping. All this you can do, and this is what is community right now trying to play with. In that process, people have found out many other physical phenomena, and the fact that you are finding many new material, new physical features, new physical phenomena suggests that you really don't understand 4 of electrons completely. Okay, therefore, with that I would like to conclude by saying the future actual molecule lies in new materials. If you find new materials, you always find new phenomena, new features. Okay, and for the benefit of young students, I would say do not ignore polycrystalline studies. The role of chemical disorder, very important. Okay, sometimes chemical disorder tells you a lot about the physics of the material, and they need to work on single crystal, thin metrostructures and nanoforms, and is not done much on condolattices. And never ignore the accidental observations. Even however, I mean, say I see only one sample, I don't pursue that. And persistence is very, very important. You know, the field is open because of persistence. In 1970, as I told you, there is only another point I didn't mention. 2000, there is another persistent thing. You have to really persist and see whether what you see is genuine or not genuine. We should not get distorted in that. And exhaustive measurements, extensive collaborations are absolutely essential with very many techniques. And it could be also the eventually key for many applications, particularly energy related. For example, thermoelectric applications, energy related. Many of the materials have large thermo power. Some of them are condo semiconductor. You can have right value of electrical transport and thermal conductivity. There are also many thermoconductive anomalies. So people are trying to look at the material even from this angle. So I would say this electron correlations on hybridization or for of localization, delocalization, I actually argue that includes even 5F. I demonstrated with 5F. It's true even for 3D. So the degree is different, but provides a lot of opportunities for progress of materials, science, discovery of new phenomena also for applications. Thank you.
So I would like to thank Professor Arun Agarwal, Pro Vice Chancellor, University of Hyderabad, for presiding this thing and for making this distinguished lecture success on behalf of the faculty members of School of Physics. And I would like to first of all extend my thanks to Professor Bindu Bomba, Dean School of Physics, for sending a concert and encouraging us to arrange this thing, and Professor Seshubai for the nice introduction. And we also thank Professor Ashok Chatterjee and Dr. Nirmal Kumar, Coordinator and Deputy Coordinator UGC CAS, for supporting this distinguished lecture. And then I would like to thank VC office for making all the arrangements, and then PRO office for making the posters and publicity. And then I would like to thank Dean School of Physics office for arranging everything. So then finally the estate section for this Raman Auditorium, and finally thank you all for the kind attention.